Today, we continue our topics, distance regular graphs and double finite algebras. So last time, we finished the part one concerning the distance regular graph part. Now we move on to part two, the double finite algebra of rank 1. First, we just a quick review what we have discussed so far. So we recall q-polynomial distance regular graph gamma that has q-Racah type. We assume our gamma contains a Delsarte clique C, and we fix a vertex x in C and construct a distance partition with respect to both x and C. And we define the algebra, say bold T, which is generated by ordinary topological algebra Tx and topological algebra T tilde with respect to Delsarte clique C. We construct a subspace of V spanned by characteristic vectors of all cells in the distance partition staircase fashion. It turns out that W is a T module. Moreover, we obtained a full Leonard system from W structure that have q-Racah type. That's what we have discussed. So this picture explains everything. Now, today's goal, we're gonna turn our T module W into an irreducible module for a DAHA of rank 1. Okay. So to this end, let me first introduce the what DAHA is. Okay. So double finite algebra. So he's Hecke. And let me give a brief background on DAHA. So DAHA is the abbreviation of double affine Hecke algebra. So DAHA for reduced to affine root system was introduced by Cherednik 1992. And that theory has been connected to many other areas like, as you see there, the integrable system and harmonic analysis, algebraic geometry. So now DAHA, this theory, became an indispensable tool in the modern representation theory. One of the well-known example, the application of this DAHA is as follows. So in 1999, Sahi extended the concept of DAHA to the non-reducible affine root system of type Cn-check Cn. And he used this algebra to prove the duality conjecture for the Corinder polynomials. Also, Norrie and Stockman treated this algebra, especially rank 1 case, in order to study the Esky-Wilson polynomials in Hecke algebraic approach. But in rank 1 case, the DAHA of type C1-check C1 is the most general DAHA of rank 1. So let me give a definition. Actually, there are several presentations to define the DAHA of type C1-check C1, but I show you the definition of the DAHA C1-check C1 in McDonald textbook. So we fix a non-zero scalars k naught, k1, k2, k3, and q in complex number C. Then the DAHA of type C1-check C1 is the associative C algebra defined by generators and relations. Our generator is T naught, T1, T2, and T3. And relations are Tn minus Kn times Tn minus Kn inverse is equal to 0 for all n 0, 1, 2, 3. Over T naught, T1, T2, T3 is equal to q to the negative 1/2. From these relations, it follows that each generator is actually invertible, and Tn plus Tn inverse is actually equal to Kn plus Kn inverse. In 2010, Ito and Terwilliger introduced a central extension of the DAHA of type C1-check C1. So the definition of HQ, let me denote the such algebra HQ hat So HQ hat is the C algebra defined by generators and relations, as you see there. So our generators are Tn plus minus 1, where n 0 to 3, and 3 relations. So Tn inverse, Tn is equal to 1, and Tn plus Tn inverse is central, and T naught, T1, T2, T3 is q to the negative 1/2. And we call this algebra universal DAHA of type C1 check C1. One of the advantage of this universal DAHA is actually this algebra has 3 parameters besides q, whereas ordinary DAHA has 4 parameters besides q. Also, it has more automorphisms. So for the rest of this lecture, we focus on the algebra HQ hat, the central extension of DAHA. Now we define elements x and y in HQ hat as follows. So our x is T3 T naught and y is T naught T1. Because each of Ti is invertible, each of xy also invertible. Now we define 3 elements, say A, B, B dagger in HQ hat. So A is y plus y inverse, that is T naught T1 plus T naught T1 inverse. And B is x plus x inverse, that is T3 T naught plus T3 T naught inverse. And B dagger is q to the 1/2 power x plus q to the negative 1/2 power x minus x inverse, that is just T1 T2 plus T1 T2 inverse. The following lemma shows a significance of these 3 elements. So take a look at this lemma. So let A denote invertible elements in any associative algebra with unity. Each of A plus A inverse, B plus B inverse is central. AB plus AB inverse is actually BA plus BA inverse. Moreover, AB plus AB inverse commutes with each of AB. So, proof, we observe that part 1, AB plus AB inverse is actually expressed as this quantity. So AB plus BA minus B plus B inverse A minus B times A plus A inverse plus B inverse times A plus A inverse. Also, BA plus BA inverse can be expressed as you see there, the right-hand side of the second equation. Because A plus A inverse and B plus B inverse are central in our algebra, so you just manipulate the right-hand side of these 2 equations, then it turns out that these 2 expression is equal to each other. So the result follows. Apply A inverse and A from the left and right respectively to AB plus AB inverse, then it becomes BA plus BA inverse. But by part 2, it ends up being AB plus AB inverse. So we see AB plus AB inverse commutes with A. We also show that AB plus AB inverse commutes with B. So this algebraic, using this algebraic property, we can say each of element A, B, as we defined earlier, each element commutes with T naught. So each of A and B dagger with T1. Over B and B dagger commute to each other because we have the relations T naught T1 T2 T3 is equal to q to the negative 1/2. So look at this B and B dagger, and B is x plus x inverse, and B dagger is q 1/2 x plus q to the negative 1/2 x inverse. So they clearly commute each other. The reason why I mentioned this commutativity is this phenomenon actually very familiar with us, because when we discussed last time the T module W, we saw that 5 linear transformations, 5 linear maps on W, A star tilde, P and P tilde. And we saw each of A and A tilde star commute with the projection P tilde. P tilde is the orthogonal projection onto the primary T tilde module. Also, each of A and A star commutes with the orthogonal projection P. That is the projection onto the primary T module mx hat. You can see, somehow we have some connection with the adjacency matrix and bold A and something like this. We recall Q-polynomial distance regular graph gamma having Q-Racah type, and we recall the parameters S star, R1, R2 with these conditions. Then we fix this square root of the parameters as square root to S, square root to S star, square root to R1, square root to R2, so that this relation we have. So with these parameters, we now construct a finite dimensional HQ hat module. And we first define a bunch of the matrices. First, for every I 0 to D minus 1, we define 2 by 2 matrices T not I. You see there, each entry of this matrix is well defined. And also, we define 2 by 2 matrix T1I. 1 to D minus 1, and 1 by 1 matrices T10 and T1D. Further, we define the 2 by 2 matrices T2I for I1 to D minus 1, and also define 1 by 1 matrices T20 and T2D. Finally, T3I, 2 by 2 matrices for every I from 0 to D minus 1. So once we define this all, the 2 by 2 and 1 by 1 matrices, for notational convenience, we use the index notation I, that is 0, 1, 2, 3. Further, we define the scalars K naught, K1, K2, and K3. So it's easy to see that each Ki is non-zero. So with these scalars, we give some properties of T naught I and T3I. So we recall these 2 by 2 matrices. Then for I 0 to D minus 1, determinant of each 2 by 2 matrix is going to be 1. So it tells us that each matrix T and I is invertible. Further, when we find the trace of each 2 by 2 matrix, then it ends up being Tn plus Tn inverse. Routinely, and this is very straightforward. And also Tni plus Tni inverse is equal to Kn plus Kn inverse times identity matrix, 2 by 2 matrix. When we multiply by T3i and T naught I, then we have a diagonal matrix. Similarly, for T1i and T2i, 2 by 2 matrices for every I 1 to D minus 1, we find the following properties. So each 2 by 2 matrix has determinant 1, so invertible. And trace of T and I is Kn plus Kn inverse. And also Tni plus Tni inverse is Kn plus Kn inverse. Lastly, T1i times T2i, it's just a diagonal matrix, routinely follows. So far, we handled with 2 by 2 block matrices. What about 1 by 1? 1 by 1 is easy. So T1i, so where our I is 0 or D, so T1i plus T1i inverse is K1 plus K1 inverse, and T2i plus T2i inverse is K2 plus K2 inverse. And also T10, T20 is square root of S star Q, and T1D, T2D is 1 over Q to the D times square root of S star Q. So we have these properties. So with this bunch of 2 by 2 and 1 by 1 matrices, we now define block diagonal matrices tau n. So tau naught is block diagonal of T naught of 0, T naught of 1 through T naught of D minus 1. Recall each block of T naught of I is 2 by 2. So T naught is 2 by 2, 2 by 2, and so on. That shape. Tau 3 is same thing, same form. Tau 3 is block diagonal matrix consisting of 2 by 2 blocks, T3 0, T3 1 to T3 d minus 1. Now, Tau 1 and Tau 2, the shape, metric shape is a bit different because T1 over 0, T1 over D, the first block and the very last block is 1 by 1, but in the middle term, all 2 by 2. Same as Tau 2. So we define our 2D by 2D matrices. We easily see that each matrix Tau n is invertible because their determinant is just non-zero. So, I want to show the matrix pattern. So Tau naught, Tau 3, 2 by 2 blocks. Tau 1 and Tau 2, first block and the last block 1 by 1, and middle blocks are 2 by 2. So now let's think about the matrix multiplication. So Tau 3 and Tau naught, and Tau 1 and Tau 2. So when we multiply Tau 3 and Tau naught, then we have exactly diagonal matrix whose entry is, you see there. Also Tau 1, Tau 2, diagonal matrix. Further, each of Tau 3, Tau naught, and Tau 1, Tau 2 is multiplicity free. In other words, all diagonal entry are mutually distinct. The proof is simple because we already saw T3I, T naught I, 2 by 2 blocks matrices. Their product is 2 by 2 diagonal matrix. So simply we compute Tau 3, Tau naught similar to Tau 1, Tau 2. And for the last assertion, each entry of diagonal entries are mutually distinct because our condition Q to the I is not equal to 1 and S star Q to the I is not equal to 1. So this guarantees that our diagonal entries are mutually distinct. Now, here is the lemma. The following 1 through 3 hold. So first, Tau n is invertible. So we actually already saw because our big 2 by 2, 2D by 2D matrix is invertible. We saw already. And also, Tau n plus Tau n inverse is equal to Kn plus Kn inverse. This directly follows from the 2 by 2. For the last condition, Tau naught, Tau 1, Tau 2, Tau 3, that is equal to Q to the negative 1/2 I. This is from the previous lemma. We routinely product these two metrics. Then we got the Tau 3, Tau naught, Tau 1, Tau 2 is the diagonal matrix, but actually, the product of these four matrices permute because each Tau n is invertible. So we got Tau naught, Tau 1, Tau 2, Tau 3 is equal to the identity matrix multiplied by the scalar multiplication of a Q to the negative 1/2. But these three statements is we're familiar with this definition, right? This is the definition of the universal DAHA of types D1 check C1. So first condition is corresponding to the first relation, and second and third correspond to the second relation and third relation, respectively. So recall the universal DAHA HQ hat. Then from this lemma, we have a representation from HQ hat to the matrix algebra met to DC that sends each generator to this matrix. So now we recall the subspace W spanned by the characteristic vectors of the cells in the staircase partition. Let the matrix Tau n represent the generator Tn with respect to the ordered basis. So by previous proposition, it turns out that our bold T module is now HQ hat module. Here's some remarks, actually this HQN module W is irreducible. We will show it shortly. This W is actually has a module structure for ordinary DAHA H. The reason is why, let me briefly explain why W has also the H module structure. Because HQ hat is central extension of H, there is the surjective algebra homomorphism from HQ hat to H, where its kernel is contained in the center of HQ hat. We just send this surjective algebraic homomorphism, just to send each generator Tn to Tn itself. Then Tn plus Tn inverse in HQ hat, its image should be, some scalar, because our HQ hat module is finite dimensional irreducible. By Schur lemma, central element acts as a scalar multiplication. So let's say Tn plus Tn inverse acts as some scalar, say uppercase K. But this Ki is actually expressed as some small Ki plus Ki inverse, because when we think of the quadratic equation, x squared minus uppercase Ki x plus 1 equals 0, because our field is algebraically closed, this equation has a root in C, but the sum of two roots should be, K uppercase Ki, and their product is 1. Guarantees that we have, Tn minus Kn times Tn minus Kn inverse is 0. So actually, HQN module induces the just ordinary H module. So it suffices to study only universal DAHA module on W. Okay, we discuss further about the HQ hat module on W. So as we see earlier, T not T3 has the form of these 2x2 blank matrices. How can we interpret on the W? Which means each T not T3 acts on W vertically. So when we apply T naught to this vector, the output is nothing but the linear combination of these two vectors. But this picture is very familiar to us because each vertical bubble represents the subconstituent subspace EI star tilde W, that is associated with the Delsarte clique. Also, T1, T2 has block diagonal matrix. So when we index rows and columns by this ordered basis, then this action exactly represents as this picture. So we can see that T1, T2 acts horizontally. That is actually the subconstituent space EI star W. So let me emphasize the action T naught T3 acts vertically and T1 T2 acts horizontally. Okay, then earlier we defined the two elements X and Y. What is the action of X and Y on W? So recall X is T3 T naught, and earlier we saw that the matrix T3 T tau 3 tau 0 is diagonal matrix. So this matrix represents our element X with respect to C. So the action of X on each the characteristic vector Ci minus hat, Ci plus hat is just this used there. So each characteristic vector is actually eigenvector of X with eigenvalue you see there. Each actually matrix tau 3 tau naught is multiplicity free, so action of X on W is multiplicity free too. Action of X on W is this, so X acts diagonally on W. What about Y? Y is T naught T1. This action is a little complicated, so let's consider the vector ci minus hat first. So now we apply T1 to this vector, but as we saw earlier, T1x horizontally, so T1 applied to ci minus is the combination of these two characteristic vectors. And then we apply T naught to each vector, then T naught x vertically. So we have this. So when we apply y to ci minus, then we have 4 terms with coefficient. Actually, when we compute explicitly, then the coefficient of ci vectors is this. Similarly, let's think about ci plus hat. So we first apply T1 to ci plus hat, then horizontally we have the combination of 2 characteristic vectors ci plus 1 minus hat. Now again apply T naught to each vector, then this action is vertically, so we have these 4 terms. So when we compute explicitly, then we have a y ci plus hat is the linear combination of these 4 terms with coefficients. So when we take a look at the matrix representation of y with respect to script c, then this matrix representation has this form. Similarly, we can obtain the action of y inverse on w. So y inverse applied to ci minus is the 4 term with coefficients, and y inverse ci plus hat, you see there the table explain the linear combination of a 4 term. Okay, so we describe action of x and y inverse. Okay, so the matrix representation of y inverse with respect to script c takes this form. So now we want to discuss the action of a on w. So we recall a is the sum of y and y inverse, but we already discussed the action of y and y inverse. So now we easily follow the action of a on each basis element. First, we apply a to ci minus. Then, as we discussed, the yellow circle represent the action of y. We saw the 4-term linear combo of these characteristic vectors. And now we also discussed the action of y inverse, that also, the linear combo of the 4 terms. So red circle represent the action of y, and green circle represent the action of y inverse. So their sum, that is the A, gives us the linear combination of 5 terms. So when we add, these all actions of y and y inverse, then we have this linear combination with the terms and coefficients. Similarly, we apply A on ci plus, and the action of y is the red circle, and the green circle represent the action of y inverse. So we just add together these 2 actions. Then we get, again, this linear combination of 5 terms and coefficients. So we discussed the action of B and B dagger on HQ-Hahn module. We recall the element B, x plus x inverse. It so the action of x on each basis, ci plus minus, x diagonally. So x plus x inverse we get easily this action, b c minus b ci plus. Further, the action of b dagger is nothing but q to the 1/2 x plus q to the negative 1/2 x inverse. From previous result, we can easily get the action of b dagger on the basis ci plus minus a hat. We also want to look at the action of this element. Let me briefly explain why we think of this action. First of all, T naught commute with A Well, T naught T1 and T3 T naught, as we saw earlier. So T naught plays an important role in this HQN module. But in generic representation theory, finite-dimensional irreducible HQN module, T naught has exactly two eigenvalues, say K naught and K naught inverse. And this HQN module decomposes into exactly two eigenspaces corresponding to K and K naught and K naught inverse. That is clearly orthogonal direction. So actually this element K naught, T naught minus K naught inverse over K naught minus K naught inverse is actually projection onto the eigenspace of T naught corresponding to eigenvalue K naught. That's why we think of this element, and action of T naught on Ci plus minus hat give us this action. Similarly, we think of this, it should be T1 minus K1 inverse over K1 minus K1 inverse. T1 minus K1 inverse over K1 minus K1 inverse. Again, T1 has exactly two eigenvalues, say K1 inverse. So this element T1 minus K1 inverse over K1 minus K1 inverse is the orthogonal projection onto the eigenspace of T1 corresponding to eigenvalue K1 in generic representation. Anyway, when we apply this element to each characteristic vector of the in our W, then we have this action. Okay, so we describe many actions of the element in HQ hat. So now I recall 5 elements in HQ hat we have discussed so far. So A, B dagger, and T naught and T1. And we describe the action of these elements on W. Also, in our previous lectures, Monday and Tuesday, we discussed the 5 elements in the algebra T, generalized topological algebra T, adjacency symmetrics, dual adjacency symmetrics with respect to X, and A star tilde, dual adjacency symmetrics with respect to Delsarte clique. And P is the projection onto the primary T module MX, and P tilde, the primary T tilde module onto the projection of the primary T tilde module MC hat. So on HQ hat module W, we discuss how these 5 elements are related to each other. This is the main theorem. Referring to the HQ hat module W, for each row, this table coincide on W. So in other words, action of A on W is actually equal to the action of adjacency symmetrics A on W up to affine transformation with some scalar, and B acts as dual adjacency symmetrics with respect to Delsarte clique C, and B dagger and T naught T1 and so on. So this is the connection between the universal DAHA of C1 check C1 and Q-polynomial distance regular graph of Q-Racah containing Delsarte clique C. So actually we already saw many actions and many big matrices. So simply we compute the matrix representing each element with respect to our the basis script C. Then we find that these two matrices exactly the same thing. So here is corollary. The HQ hat module W is actually irreducible because our algebra T is generated by these 3 elements. And also the bold T module W is irreducible, we saw yesterday. So by this theorem, HQ hat module W also irreducible. Okay, so let me summarize what we discussed. W and affine transformation, up to affine transformation, our element T naught T3 plus T naught T3 inverse, T3 T naught plus T3 T naught inverse acts as the adjacent matrix. T naught T1 plus T naught T1 inverse acts as the dual adjacent matrix with respect to Delsarte clique C. And B dagger T1 T2 plus T1 T2 inverse acts as the dual adjacency matrix with respect to vertex X. Further, T naught acts as the projection P tilde, and T1 acts as the projection P onto MX hat. This is the main result of my okay, so I think this is natural starting point. So let me start here.
May I see the screen with the matrix Y?
Action of Y. Matrix Y.
That one with the 6 half.
This is Y. This one.
Now go to the inverse. Now go to the inverse.
Oh, the inverse. Okay. Yes, slightly different.
Like in this has the structure, the same structure as the transpose of the joint of Y.
Yes.
Well,
yes.
do you know if Y minus 1 is the adjoint of Y? I mean, it is unitary, or at least clearly related to minus 1 and transpose of our adjoint are more or less the same for this matrix. It seems that there should be a relation between inverse and adjoint. But I'm not sure.
Could you go back to the definition of Y?
Y is just the T naught T1.
Yeah.
So you mean the Y inverse adjoint of
Could be the adjoint of Y,
oh
or at least would be period relation. Times apart, could be. And I believe it's going to be the other comment. I check that.
Oh,
because
okay.
if this is the case, this connect you with another with the same time connect all this stuff with very little things. Once you answer my question, then you would talk to me about CMB matrices.
Oh yes, but CMB matrix, I have seen that, but that is the infinite case, right?
No, you can have finite first.
Oh,
So it can be ready.
okay.
So if this is the case, you are dealing with finite CMB matrices. Like finite the Hecke matrix. You talk about the Hecke matrix, you're talking typically about semi-infinite diagonals in the matrix. But the CMB matrices are the unitary analog of the Hecke matrix. And they have this shape that you have there. And think Y minus 1 seems to be close to the adjoint.
Yeah.
If that's the case, and Y is unitary, then you are entering another phase and connecting this with many other things. If this is the case, this is an open way to many other areas of mathematics and physics. Also. That's a comment. If you are like that, things are what I'm saying. You have a bridge.
Okay, thank you. Thank you.
Let's see, Jae-Ho, can you remind me? So in the algebra, so in the DAHA itself, that algebra. Well, let me say it more quickly. So we don't expect that the transpose of Y here is actually represented by something in the algebra, but there should be some anti-anamorphism of the algebra that sort of plays the role of transpose. I mean, it's roughly analogous to the transpose. Now, I forgot. So do you have an anti-anamorphism of DAHA that you use? Order to?
I tried to make the anti-automorphism to apply element of this one, but I don't remember exactly, but I didn't get anything.
Oh, okay, so in your original paper.
No, I didn't mention about the anti-automorphism. The anti-automorphism, what I understand is used to obtain the other other representation like Corwinders or Zhdanov, they define the Dobrov-Hecke algebras. To get that representation, we apply the anti-automorphism to this definition. So may get the same representation, but I'm not sure that anti-automorphism is what you mean. But this matrix shape appears in other areas. So yeah, thanks for your comment. Take a look at that.
It appears in many other places.
Yeah, if I understand correctly, you give an interpretations of some sub-algebra of DAHA in the Théorie algebra. If I understand correctly, you give the A, and the A, but we have an interpretation of the TI of the DAHA in the Théorie algebra.
That's a good question.
If I take the representation, TI,
yeah, that's a good question. That's open problem. Well, in here, we just describe the relations, the actions, but we don't know exactly what's the image of the generator of HQ hat in this T algebra.
I expect more kernel or something. I expect those are no interpretations. More the sub-algebra or the DAHA, which makes sense somewhere.
Maybe I'm not sure. So so actually I have thought about that problem. So actually this relationship is true only over W, not the whole space. So if we extend this module structure for the whole space, then I might answer for your question. What is the image of
I'm not sure that the A, B, and B. If I take only the generators word here, is it isomorphic? It's a sub-algebra of the DAHA, or it's really the DAHA algebra? If I take the
this is the elements in original algebra. DAHA, yes.
Some elements that generate all the algebra or just the sub-algebra of the DAHA. Because it's not the generator. You show us the generators of DAHA with some T or some K, I forget. And A and B and so on, some quadratic element on the kind.
So
the big A.
yeah, so
I'm not clear.
presumably, probably, the elements bold A, bold B dagger, T0, T1 generate a sub-algebra of the HQ hat. Not the whole thing.
Okay.
For sure.
Like I expect.
Yeah. Any other questions or comments? Okay, let's thank Jae-Ho again.